Hi viewers, welcome to our electrical engineering lectures channel for most interactive sessions of different subjects of electronic and electrical engineering. For the latest updates and videos, don't forget to subscribe and click the like button.
Assalamu alaikum everyone. In today's lecture of digital communication, we will be discussing the concept of equalization in digital communication system. So whenever we talk about equalization, first of all we need to review the receiver structure that every digital communication system has, and to have a quick review and glimpse of the receiver structure, let's have a look at this block diagram which we have already discussed in the previous lectures. We see first of all the received signal passes through the frequency down conversion stage, which converts the passband signal into the baseband signal. So at the output of this frequency down conversion stage, we have the baseband signal. The next stage is the receiving filter, which is usually in the form of a meshed filter, and after passing through the meshed filter, it passes through the equalizing filter. So the meshed filter is usually designed in order to have zero intersymbol interference, but due to the timing errors and problems in the timing synchronization, usually it is not very ideal that we have zero intersymbol interference. So in practical cases, we have channel induced intersymbol interference, and to mitigate that intersymbol interference, we need to have the equalizing filter. So due to this reason, almost in every digital communication system, equalization or equalizing filter is a mandatory stage that we need to design in order to mitigate intersymbol interference. So now let us discuss what is the concept of wireless channel and why we need to have equalization. The first reason I have already explained, that to mitigate intersymbol interference, but as you should know that every wireless channel can be modeled as a linear time invariant system, and every LTI system has a certain magnitude response and certain phase response, as shown by this particular transfer function, that if the channel has a frequency response shown by hc of f, then it can be split into two components. The first one is hc of f magnitude, which is the non-constant amplitude or amplitude distortion. What is meant by non-constant amplitude? It means that this magnitude response will not be constant for all the frequencies. This is called frequency selective fading. So we need to cater for this non-constant amplitude distortion. And the second part is the phase response, denoted by e raised to power j theta c of f. This is a non-linear phase, or we can also say it phase distortion. So every wireless channel introduces two types of degradations. The first one is the non-constant magnitude distortion, and the second one is non-linear phase distortion. This phase can also be linear in certain cases, but generally speaking, this phase distortion is usually non-linear. To have further graphical understanding, I will show you two examples of different channels. The first example is of a channel which is frequency selective and slowly changing or slow fading. Frequency selective means that the channel will behave differently for different frequencies. So this plot is showing you a 3D plot in which this axis is corresponding to the channel amplitude, this axis is frequency index, and this is time index. So if you see along the frequency index, you can see multiple and different variations in the amplitude. So it means that signals having different frequencies, or a single signal having different frequency contents, will undergo different types of degradations or different amplitude degradations. Due to this reason, such channel is called frequency selective. But what is meant by slow fading? It is a totally different thing. We have to see along the time axis. If you see along the time axis, you see all the variations along the time axis. If you just slice this 3D plot along the time axis, you can see that the variations along that particular slice are constant. So due to this reason, such channel is called slow fading channel. So these type of channels are usually easier to compensate. But if you see the second example, which is also frequency selective, and at the same time it is fast changing or fast fading channel. Fast fading means it introduces the amplitude variations in both the frequency axis. You see along the frequency axis there are certain amplitude variations, along the amplitude dips also. These dips correspond to those frequencies at which the channel produces nulls, and this is a very serious and critical type of degradation, which is very difficult to handle in practical situations. And along the time axis, you also see again there are variations along the amplitude. So in this particular example of the channel, you cannot see any slice along which you observe constant amplitude variations. So another aspect to have a look at the channel degradations is the famous eye pattern or eye diagram. First of all, this is an eye diagram of non-ideal channel in the absence of AWGN or noise. You see, in this particular case, since there is no noise, so we are not seeing any kind of distortions along the amplitude scale. The eye diagram is fine, clean, but due to the presence of intersymbol interference in this PAM example, you will observe that this eye opening is not very clear. So due to this reason, it will be very difficult for the receiver to detect the correct symbols. And in the same example, if you introduce AWGN also with EB over N0 is equal to 20 dB, and in the presence of ISI, the same eye diagram will be degraded or distorted as shown by this particular eye diagram. And if you decrease signal to noise ratio or EB over N0 and to change it to 10 dB in the presence of ISI, the same eye diagram is now very much distorted, and it is very much clear that if you draw a threshold over here, it is not possible to detect the correct symbol +1 and -1. So this is the consequence of the introduction of intersymbol interference in the channel, and due to these reasons we need to have equalization stage. So that was the significance that why we need equalizing filter on the receiver side. And to have a block diagram representation, this is the same block diagram that I have already explained in the previous lecture of intersymbol interference. You see the overall transfer function from end to end for end-to-end communication system is shown by this particular transfer function, in which Ht of f is the transmit filter, Hr of f is the receive filter, which we have already designed to have the root raised cosine, and rather to be more specific, square root raised cosine on the transmitter side and the a squared root raised cosine filter on the receiver side, so that the product of these two becomes root raised cosine. Now this is the Hc of f, which is the channel transfer function. Now if there is no ISI introduced by the channel, then we do not need to have equalization. But since due to the timing errors and problems in the timing synchronization, there will be ISI introduced by intersymbol by the channel, and due to which we need to have another equalizing filter here at this point denoted by He of f, so that this He of f cancels out the contribution or degradation introduced by this Hc of f. Let me show you more specifically over here that the overall transfer function from end-to-end digital communication system will be Ht of f multiplied by Hr of f and multiplied by Hc of f. Collectively, the product of the first two frequency responses is denoted by raised cosine filter. And because raised cosine filter completely eliminates the intersymbol interference at the sampling at the integral multiple of sampling instants, so we desire to have this much frequency response as the equalized frequency response. But due to the introduction of this Hc of f, it will be no more equal to Hrc of f. So to balance things out, we need to have another equalizing filter over here, so that these two filters cancel out each other, so that He of f must be equal to 1 over Hc of f. So these two systems must be inverse of each other, so that these two are cancelled out, and we are only left with the overall transfer function as Hrc of f. Now this was just a mathematical description of the problem, but to have a clear understanding, let us look at the impulse response of the raised cosine filter. If we have no ISI, then the impulse response of the raised cosine filter can be drawn as like this. So this is 0, this is capital T, this is 2t, and so on, and here it is -t, -2t, and so on. So this is basically Hrc of t. So you see at the sampling instance, it is straight away equal to 0. But now, due to the introduction of the channel, this impulse response will no more like this. It will be a different thing, and at the sampling instance, it will not cross the x-axis. So it may be like this, it can be like this. Let me draw just for an example. It can be like this. So you see at this particular time, it is not crossing the x-axis. Similarly here, and here. So at these times, at the integral multiples of the timing of the sampling period, it is not crossing the x-axis. Due to this reason, intersymbol interference will be introduced, and the purpose of this equalizing filter will be to remove or mitigate this intersymbol interference. Now we will see how can we achieve and how can we design the equalizing filter by multiple methods. So we can always categorize equalization into multiple types, and the broad classification of equalization is into two types. The first one is MLSE, which is maximum likelihood sequence estimation. This maximum likelihood sequence estimation is completely a statistical method, and it involves maximizing the likelihood function of the received signal so that to minimize the intersymbol interference. But we will not go into the detail of this maximum likelihood sequence estimation in this particular lecture, because the purpose of this lecture is only to discuss the linear equalization, which falls in the category of filtering. And under the category of filtering, we can have further three different types of equalization. The first one is transversal filtering, and it further contains two types: zero forcing equalizer and minimum mean square equalizer. So we will discuss these two types in this lecture, and also we will shortly discuss decision feedback equalizer, which is basically a non-linear equalizer. So these two categories are linear, and this is categorized as non-linear equalizer. And the third type is adaptive equalizer. So these three types fall into the category of filtering based equalization. So first of all, now let's have a look at the equalization based on transversal filter. The main concept of this transversal filter is that we pass the received signal, which contains intersymbol interference, through a filter having finite number of coefficients, so that the output of this filter contains no ISI. To perform this operation, we need to transmit a known signal, which is in communication system it is called a training sequence or preamble. And usually this training sequence or preamble is designed in such a way that it behaves very different as compared to the payload or the actual transmitted data. Usually it is in the form of pseudo-random noise or pseudo-random sequences whose time domain response is similar to impulse, as you should know that the impulse response or the autocorrelation function of the noise is usually in the form of an impulse function. So we transmit a known data. So the main thing will be that we transmit known data, so which receiver already knows. So when that known data passes through the channel and then it is passes through the transversal filter. So at this point z of k, you can say it is known. So by using this known signal, we will find out the suitable values of coefficients that are needed just to mitigate the intersymbol interference. So actually you can say that we know the output and we know the noise corrupted or ISI corrupted data, which is shown by x of k. So by using these two combinations, we will find out the suitable values of these coefficients needed to cancel out the intersymbol interference. So as a general model, you will see that we can have any number of coefficients, but this particular model uses 2n+1 coefficients, starting from c minus n plus 1 up to cn, and in between there will be some c0. So we will have a total of 2n+1 coefficients. In order to have a known output of this transversal filter, we will reverse engineer the coefficients needed to mitigate the intersymbol interference means it will force the impulse response of the data so that it becomes 0 at the integral multiples of the sampling period. So as you can consider this to be an LTI system, let us look at the block diagram level. If x of k, so let me place an heading over here. Transversal filter. If x of k is input to this transversal filter having coefficients of Cn and the output is z of k, so this z of k is known to us. So if this is the case, then from the theory of LTI systems you can always write z of k as the convolution of Cn and x of k, or mathematically we can also write z of k as summation. If you open up this, n from minus n to capital N, and here x of k minus n into c of n, where n is from minus n to n, and k can take on any values. It can take on any values as it is running time index. So this is the main equation that governs the operation of this transversal filter. To further have a clear understanding of what this equation actually means, just we can start putting values of k, and just for simplicity we can consider the values of k from minus 2n up to 2n. So these are the time samples. So if you place, let's say k is equal to minus 2n, so what this equation comes out to be, so it will be z of minus 2n equals summation minus n to n x of minus 2n minus n into Cn. Similarly, we can place, let's say k is equal to 0 after some values, and then z of 0 will be equal to, again the same summation, here x of 0 minus n Cn, and similarly for the last value we will have k equals 2n, so it becomes z of 2n equals n minus n to n x of 2n minus n into Cn, and for all these values n will be from minus n to n. Now if we put the values of small n in all these sub equations, we can formulate it into a matrix form, so that the vector z, it will become a column vector such that it is from minus 2n, somewhere in between it will be z of 0, and the last will be z of 2n, and the coefficients c vector will be c of minus n, somewhere it will be c of 0, and the last will be c of n. And what about the vector x? If you put the values of k and n into both these, so x turns out to be a matrix. It will be a big matrix. It will start from x of minus n. As an example, let me show you how it comes out to be. It was x of minus 2n minus n. So if I place value of n is equal to minus n, what it comes out to be, x of minus 2n plus n, which is equal to x of minus n. So the first sample of this row will be x of minus n, and then the next one, if I put value minus n plus 1 into this, so it comes out to be minus 2n plus n minus 1. which is equal to x of minus n minus 1. So the next one will be x of minus n minus 1. Similarly, it will go up to the last sample, and along the columns, the next sample will be minus n plus 1, the next one will be minus n, and so on. And somewhere in between it will be equal to x of n when k is equal to 0. This particular thing correspond to k is equal to 0, and the next one will be x of n minus 1, and so on. And you further extend this downward. Similarly, on the right bottom side, we will have the samples over here as x of n minus 1, and here it is x of n. Now if you see the dimensions, but before seeing into the dimensions, just I will describe you the generic method to write this particular matrix. Starting from x of minus n, here at this point, if you move along the right, you will decrease by 1. You will decrease it by 1. So if it is x of minus n, it is x of n minus 1, you are decreasing. And if you are moving here on this direction, you will increase by 1, right? So in this way, you can formulate this particular matrix. And what about the dimensions? This particular z vector will have dimension of 4n plus 1 cross 1. This matrix will be of the dimension 2n plus 1 cross 1, and this particular matrix will having dimension of 4n plus 1 cross 2n plus 1. So having all these dimensions and from this particular equation, let's say we call it equation 1, not this one, the generic one. So equation 1 can now be written in the matrix form. Equation 1 can be written in matrix form as z vector equals x vector multiplied by c vector. So this is the closed form expression. Now just come to the original point, which was that we actually transmit a known preamble or training sequence. So this is known. If this is known and this is the received preamble, then we can easily compute this c vector. So just writing in the form as c is equal to x bar inverse z. So this is the main equation, how to compute the coefficients. But there is a problem. There is a problem in this equation. If you closely look, how can we take the inverse of this matrix? Because in our modeling, this matrix is not a square matrix. So this equation can only be considered if X matrix is a square. So because there is not a square matrix, therefore we need to make it a square matrix. This problem will be discussed shortly in the zero forcing equalization. Anyways, this is the general solution, that whenever we are going to equalize, we are going to design an equalizing filter using transversal filter. The first thing is to compute the vector of coefficients c bar, and when we have computed the vector c bar, then we will use this c bar into this equation, so that it can be used for any incoming data to mitigate the intersymbol interference and perform equalization. Okay, so that was the general discussion about the transversal filter. Now we see the basic two types of the linear filtering using transversal filter. The first one is zero forcing equalizer, and the second one is MMSE equalizer, minimum mean square error equalizer. The first one is zero forcing. What is meant by zero forcing? As the name is suggesting, this equalizer aims to force the output of the equalizer equal to 0 at all the integral multiples of the sampling instants except equal to 0. So except at the peak of that raised cosine filter, it forces all the all the values of that raised cosine filter at the integral multiple of the sampling instance. So what does that mean? It means that we have to adjust all the coefficients of the equalizing filter so that the output of the equalizing filter becomes equal to 1 for k is equal to 0, which is corresponding to the peak, and it is equal to 0 here for all the integral values of k plus minus 1 up to plus minus n. So that is the main theme of the zero forcing equalizer, right? So now let us discuss it more over here.